without further ado, I am delighted to introduce ASE Hjorth Larsen. Hopefully I haven't butchered the pronunciation too badly. He's from the Technical University of Denmark and has been involved for a long time in the atomic simulation environment. One thing I should have said is many of the tools you'll hear about today have already been mentioned yesterday in some form or another, ASE very much among them. Yeah, he'll tell us a little bit about the tool and I think something about the sort of development narrative, so to speak, and maybe even point out some further potential for kind of synergies and collaborations beyond what we've already talked about a little bit. So without further ado, thank you again and take it away.
Thank you very much. And also thanks for organizing the conference. I enjoyed getting an introduction to Julia for the first time. In this talk, I'm going to give a brief overview of ASE. Probably most of you know it, so it will be very brief. Then I will discuss a little bit the history and how things have changed over the years. And then I will go a little bit more into detail about particularly project level infrastructure and testing and the things that we do to actually maintain it, which is a significant challenge. So that's roughly the scope of the talk. And so I hope that, that you will also have some questions. I probably will not be saying all of the things that everybody wants to hear, so please feel free to interrupt, and I can also browse a little bit around and show how things look if need be. So anyway, the atomic simulation environment is a Python package which is designed to set up and control atomistic simulations. And the most well-known feature would be the atom subject, which represents a structure. And the atom subject would then have chemical symbols and positions and knowledge of a possible unit cell. And it can also have a calculator, which would be a way to evaluate energies and forces and other things. Then ASE has a number of structure builders to help set up simulations. There is a large number of I/O formats. So one can read and write a lot of both standard formats like XYZ and cube, and but also formats pertaining to specific DFT codes. And there are the calculators, which are these interfaces to codes, or it can either be external codes, or it can be something that's implemented in Python, or it can be something else, as long as they do energies and forces and probably some other things. Then there is a large collection of algorithms that can work together with atoms and calculators. So one can run structure optimizations and dynamics and a lot of other things. But most importantly, having high-level control via a scripting language means that you would just write your own driver and do your own thing when you need to. So historically, I didn't think that much of ASE in the beginning when I started at the Technical University many years ago, because it was just a trivial idea to kind of do this calculation, and it's probably not even very efficient and stuff like that. So it wasn't really until I moved to another group and there was no ASE calculator. Then suddenly that was very annoying. So I grew up with ASE and everything was easy for the code that I was working with, and then now we do have an octopus interface for ASE. So yeah. There is also a graphical user interface, so one can open and rotate and do simple manipulations. It's not extremely advanced, but it is pretty simple, and I think it works well. And there are a lot of other little tools for different things. So ASE is really a big Swiss Army knife. The core parts, there are the core parts, and there is a large collection of additional little things, some of which are probably a little bit unused and maybe unmaintained. So the place where ASE fits into the typical software stack that we would be using in computations, some would call it kind of middleware, that there is a user somewhere on top and maybe some workflow software that controls like large sets of calculations. And then there are some scripts or library calls doing these simulations. Maybe they code some optimizations or some custom displacements or anything like that. And that would then be coded in terms of ASE. And ASE uses a classical Python scientific stack, NumPy, SciPy, and Matplotlib. So one has that at one's disposal. And then if you are using ASE for computations, it will be calling these DFT codes or force fields codes, which are often written in Fortran or in other languages. And they will then be calling things like MPI and FFTW and other high performance libraries. So ASE is not really a computation library. The purpose of ASE is really to set up things and perform high-level control. So high-performance code would not normally go in ASE. Sometimes you get some things that are a little bit, could use some optimization, and that can be annoying for people working with large systems. But mostly we try to keep the infrastructure simple, so we don't get we don't end up depending on a lot of infrastructure for compiling and other things. So back in 2002, there was an article which was like the original reference article for ASE, an object-oriented scripting interface to a legacy electronic structure code. The authors have created an object-oriented scripting interface to a mature density functional theory code. So mature is a little bit a code word here. It has matured, but then the people who wrote it left, and it became difficult to work with. And also being written in Fortran, it was any new thing would require a lot of familiarity with this code base. So the idea was to make a kind of socket interface so one could use a Python process to control it, and hence write scripts where one previously needed all kinds of run modes and strange constructs. So the code that it was an interface to was the capo and ultrasoft pseudopotential code, and it's so old that I never used it. So, but that was for many years the reference article, and then even though this worked well, apparently it was not sufficiently good to become really popular, so it was mostly an internal thing at the time. Then at some point it was rewritten into something called ASE2, and that then added a very high level of abstractions. So there was a lot of complexity in the end due to having to be specific about wanting the Cartesian coordinates, for example, and there were, everything would try to take into account everything, and it would be a little bit too much, because in the end often you just need the bloody positions. And I think it was living in a CVS version control repository, and it was also a little bit before my time. So when I started, we could still use it, but I was just a student at the time. So then came ASE3. So this was Jens Jørgen Mortensen, who is the historical main character of ASE. So he wrote in 2007 ASE3 because the ASE2 was a little bit too clunky. And so this made the data model more tangible, so one could get the arrays and things would not be behind so many layers of abstraction. The code base was moved to SVN, which was modern at the time. and the documentation, which was previously a Moin wiki, was then moved to Sphinx, which is Python's own documentation system. So it had recently become available at the time, I think. So in those years, it was mostly still local people who were working on it, but there was an increasing number of people from other universities, and sometimes adding these calculator interfaces, such as Siesta and Abinit. And then eventually, Git became kind of an interesting option, because it was not so nice to work with SVN, because you commit something and immediately it's there for everyone. It's not so, one cannot just do code review, or at the very least at the time we did not have any such process. So the more people were there, the more things would likely break. And so we moved to Git and GitLab, which was new at the time, in 2015. And then suddenly everything changed, because since this followed a distributed development model, not everybody had to be added to some central SVN repository, so people could just do forks and make some changes and open a merge request, and things became incredibly busy. So so we had to do a lot of work doing review, and we had never really done that before, and also a continuous integration pipeline was added, and that was kind of where I started to take over a little bit, because it was too much work for Jens Jørgen to take care of it all. So eventually I became the maintainer, and then over the years we probably added more features than we should have. One must also say that at the time it was not so easy to write new little projects. But that became a lot easier when PyPy became more well established. So there was this packaging system, and one could do like a small package and upload it pretty easily. That was not the case at the time, so all kinds of student project code was crammed into the project, since it had nowhere else to go. So that was solved. Then we published a new reference paper back in 2017, and many years overdue. Finally, in 2019, we had the first users and developers meeting. I suppose it's a little bit because there is no kind of very central institution with funding that is responsible for ASE. It was always more like personal motivation and let's do this, but at an informal level. So at the very least, those years I was very interested in it. I would spend all available time, but most DFT codes that are actually backed by PIs with fundings, they will have like publications pretty quickly and workshops and so on. But we only did it recently. Then we dropped to Python 2 support and did a lot of kind of maintenance work, because things were starting to, it started to become clear that there was so much in the code that was old and maybe not needed. So a lot of cleanup was done at the time. So we had this custom test suite that was based on every test being a standalone module, which is not very nice because you get very long tests. And then we switched to PyTest, and that was an incredible improvement. A lot of old scientific code, like much of ASE has been gradually adapted over time, because it was added by people who didn't really know about testing and best practices. Some tests might set an environment variable, then it would be visible in later tests and so on. A lot of work on that. And the test coverage was barely at 50%, I think, when we started. And not all of the calculators were actually working, because there would be new releases of these codes. So a lot of the maintenance work that I have been doing since is to try to improve the testing infrastructure and get it to run with Dockers and continuous integration, so we can trust that everything works all the time. And so the situation now is that we have managed to increase by 25% the code coverage, but a lot of, so I'm talking about the code coverage in CI, because there are plenty of tests of VASP, for example, but a lot of it requires VASP to be installed, and we don't have that in CIs, and maybe we don't have licenses for all of the proprietary codes, so an unknown amount, we have no way of telling how much. An unknown amount of code may not really be working at any given time, but somebody normally comes along and fixes it. If you go to the ASE web page, so nowadays we have it in Sphinx, still hosted on the DGU page, and there is actually a fair amount of documentation. Some people have historically cared to get documentation written for most of the features. So even though it's incomplete and probably has inconsistencies, I would say that it's quite good for typical scientific software. At least that's what people say. And you can see also here an example of how to run a calculation using NWChem, assuming NWChem is installed and configured. And you can see that there are a lot of, it's quite large in volume, the documentation. Then we have the GitLab repository, and one of the funny things is that ASE can do so many things, but probably people want to do things slightly differently. And there are a few design decisions that make it a little bit inflexible. You might need to edit the code in order to do things differently, instead of like adding a function in your own script and being able to use it. And I suspect that it's there, that it's for that reason that there are so many forks. So this is not GitHub, but rather GitLab. So there is actually a much lower number of users. So these numbers would be higher, at least the number of stars would be higher on GitHub. The number of forks I'm not completely sure about, because people would presumably have a reason to do an actual fork. But there are 800 forks. So it tells us that a lot of people actually clone the code in order to do some minor change, because it was not precisely what they wanted, but pretty close. But most of them are never integrated again into the code, so I actually don't really know why that happens. If somebody has some input, they would be welcome. It's interesting to discuss. And of course, I recently updated this screenshot so it would have the latest coverage rating. Anyway, almost all of the development takes place on GitLab. So we would create issues and open merge requests and discuss it there, and then hopefully merge it eventually. So the actual Git repository, well, it's all written in Python, and there are 192 contributors now with at least 5 commits each. And here we have like a graph of number of commits as a function of contributor index. So every unique person, I have tried a little bit to sort out duplicates. Many people have only one commit, and but a few people have a moderate to large number of commits. So I'm the one who has the largest number now, and number 2 is still Jens Jørgen, and I'm not completely sure about the rest. And so in principle, I'm now the benevolent dictator for life of ASE. We don't actually do that much kind of, it's a very small and informal group of people who actually do the maintenance. So we mostly get contributions and fixes from random people at different institutions, seeing whatever, and then we might merge that or ask for a test or something like that during code review. But nobody really has a lot of time to think big and say, where should this project go? I have a lot of opinions, but I don't have time to do much about it. So things remain very much status quo. So if we had a lot of time, then we could maybe do something about it. That would be nice. So I will discuss a little bit later some of the design challenges that we have that it would actually be nice to do something about if we had more time. So, but some of the particular challenges for ASE is that in order to test all these code interfaces, they are quite expensive to run. So we easily get a test suite that it takes a long time to run. And it also requires those codes to be installed. And of course, we cannot really test the proprietary codes, at least not in a system that can be triggered publicly. That would allow other people to perform arbitrary calculations, conflicting with the license probably. The other thing is that we have a lot of code now, and it's simply a large volume and difficult to. We can ignore it, but it's. I would prefer to have a small code base where I know what's going on. And so part of that leads us to our current primary focus, which is to say, how can we split this into components that are maintained by different people? So the other thing is that since ASE has grown a little bit randomly, depending on what people needed, what kind of simulation, we often get these improvements or features that they do the job, but they're maybe not the best designed. And the main problem here is that there is no central definition of what is actually really public, and so what are people supposed to call, such that we cannot change it, and what is internal processing so that we can change it and people should not call it. So that makes it very time-consuming because we don't actually know the repercussions of changing something, and often there are very subtle little things hiding under the surface, particularly in parts that are not well tested. So in Python, it's very easy to access data on objects, and we have not really tried to make the attributes private, and that might have been good for some things, but it also bites sometimes that we actually have no clue how to what things can be updated, or we need a lot of time to guard against breaking things. And the final one is that the ASE calculator interface is mostly thought as a way to communicate about forces and energies and a few other things that this code might produce. But DFT codes are so different, it's not so easy to make a protocol that covers all use cases. So many of the calculators have become big classes that have a lot of stuff added to them doing different things. And some of them can talk directly to Slurm, and some of them can do other things. And that makes them cumbersome to work with, and we cannot change things, because if we change the overall infrastructure, we will break 5 calculators or 2 calculators or some other unknown number. So but the main tool that we have to actually facilitate changing the code are the tests. And so, in spite of my gripes about it, it is actually a quite good test suite that we have had historically, because Jens Jørgen Mortensen was very keen on adding tests back in the beginning, and we taught people to do so throughout the years when writing new features. And as I mentioned, we use GitLab now for continuous integration testing. And then there was the very essential big move to PyTest from a few years ago, which means we have, it's a much more modern and comfortable to work with test suite now, but it still has some elements of these tests that are a little bit too large or too much focus on integration testing. And then, I'll talk about Dockers in a moment. Anyway, so the actual CI configuration defines a lot of different test jobs. So there is one called old libs, which tests everything with the latest, with the oldest versions of everything that we support. So it will be an old version of Python, and it will be old versions of NumPy, and that's kind of the lower bar for what we want to work with. And then there is a one called main that has all the newest stuff. Then there is a separate job running on Windows, probably with all the newest stuff. Some linting and building the documentation. And then there is one that installs everything or has a more recent dependencies, which is based on a pip install and not, so it can be updated more easily than the others, which are generally based on Dockers. There is also a calculator's job that takes a long time to run, and the calculator's light that is actually running on any merge request, so those should be fast tests. We have done quite a lot of work to get a good trade-off between how many CI minutes we can spend and versus what we can test. Then there is some kind of coverage, code coverage measurement, and some deploy stage that puts the statistics on it. So that's basically the configuration. To actually test the calculators, we have like PyTest fixtures. So fixtures are like a PyTest feature to reuse initialization or clean up code across many tests. So we have a number of these factory objects so we can create calculators differently in different tests. And this has been added for all of them in one form or another. And then we also need, in order to test all of those codes, we need all these Dockers that must then be compiled. So we have a GitLab repository somewhere called ASE Dockers, I think it is, and it has all of the Docker files and all of the compilation to build these Dockers. So a Docker is a software container which you can install stuff on it, and then you can kind of run it inside another computer. So we could run the tests on our own runner or on GitLab's runners. Currently we use GitLab's runners because we have on GitLab, if you're an open source project, you can apply for special gold level support, and then you have almost unlimited pipeline minutes. Otherwise you quickly end up needing your own runner, which is, however, not a bad thing to have. So this is how we build these software containers. There is a system of scripts that builds them, reusing parts from such that each is built from the previous one. So it starts with a Python base image, it's probably 3.9 now, and it installs a lot of compilers and libraries that are useful for all of the codes. Then it does some apt-get install, so it can get as many as possible of these external codes that we have interfaces for installed in one go. And then we have a lot of of custom little Dockers that then copy over some they are kind of extensions of the build tools Dockers, each of them installing a single code somewhere. And then one Docker to have all the Python stuff, so that's where the main tests run that just test the type Python stuff. And then one called Full Monty, which pulls all of the installed code from all of the other Dockers. So everything is on one Docker, and that one can run with any calculator. At least all of those that we have been able to run. And that's kind of not considered good Docker design. You should do small Dockers, each of which does one thing. But then each of these Docker images that we would need become so large that the GitLab runner spends a lot of time downloading it, and it would be bad for the environment and other things. So, so the current situation is that we have this full Monty Docker where all the calculator tests run. And okay, so I'm going to change a little bit now. Maybe I should ask if there are any kind of questions so far or comments. Mm-hmm.
I was just curious if like the Docker test can work with NVIDIA, or if this is only fun like CPU.
So we run on GitLab's shared runners, and they would probably not put GPUs at the disposal of somebody who doesn't pay a lot of money. But actually for GPOR, the GPOR code, which we also work on, there we have set up, but that's a TFT code, so it does actual number crunching, and it has really a lot of integration tests. So it takes a long time to run those tests, and they must run in parallel and on many different, in many different ways. So, so that's expensive, and therefore, not so long ago, we set up, like a couple of years ago, we set up a CAMD runner. So that would be an old supercomputer node, and we installed GitLab runner on it, so it can pick up jobs. And then we configured the project to pick up, to let it pick up its jobs. So now everything runs on that. And so this means that one, actually that one does not have a GPU, but we set up a different one which has a GPU. And that was not enough because GPUs of different types are also not working well together. There are many catches there. So in order to be able to support both NVIDIA and AMD, we actually we are working with people from CSC that have to do with the Lumi supercomputer. So we actually have a runner set up that with appropriate authorization can trigger a job that is submitted to Lumi. So, so that way, I mean, for GPUs, it's essential that you have your own hardware. And one of our lessons from working with GPUs was also that it changes so frequently and in so subtle ways that if you cannot test it, you will get nowhere. So you would work for months, and then suddenly you wouldn't know that now it broke a long time ago on some other systems. At least if it's something as complicated as a DFT code where you do many different things, then it's really essential to have many different pieces of hardware.
In practice, how often does this I guess full Monty one end up being run?
All of the time.
Wow.
So any merge request or any push will have it run the test suite on the full Monty Docker, but only doing the calculator's light job. So that means it will do things like H2O and silicon and some other simple things. And it's not enough to make sure that all of the calculators work. At any given point in time, lots of things may be broken, but at least forces and energies and other things, the socket interface, we have generally that under control. So It takes about 10 minutes or so. So actually, if we go here, GitLab, we can see roughly how it looks. So there was some merge request, and then it ran a pipeline, and then we can click on the calculator slide, for example. And so that runs all of the kind of fastest tests, and it only takes apparently, no, this is actually the test script. 4 minutes. That's suspiciously fast. So I would have suspected that we were not properly testing something, but the code coverage is still reported as high, so I suppose we can trust that it's. I mean, I have done a lot of work trying to make all these tests run in as few seconds as possible. A lot of contributions that we get, they will have a test that takes 2 minutes to run. And that's just, you can't do that because you will very quickly get a code base that you get a feedback loop that is an hour long or 2 hours long, and then you need to move a lot of it to only be nightly tests or something like that, and it's really clunky. It's much nicer to have these tests that are, you spend time doing good tests that are fast, and then you save time because the whole project runs much more easily. I think I digress a little bit. Other questions? I think I should finish relatively like 10 minutes or so.
Yeah, thereabouts.
So there are also plenty of overall design things pertaining to the different features in ASE that it is worth discussing, or that we have been thinking about, because every now and then there needs to be some kind of major update to clean up all of the mess and all of the duplication, because we hadn't quite done the thing the right way. And one of the current challenges is that we have this ase.io.read, which is like an overall interface to reading any format. And it does a lot of strange things, like it's easy to get parallel deadlocks because it assumes that it runs on MPI world if you are doing MPI, which is rare. And it can also guess if it's a compressed file and try to uncompress it, which makes things a little bit faster, but it's also really complicated. And the other thing about the I/O formats is that they generally take atoms as an input and save that to the file, and then when you read the file, they return atoms. And that's of course incredibly easy, but it's also a big problem sometimes, because if you have a format that can store something that's not defined on atoms, then you need to kind of mesh it into the atoms. And of course you can do that because there are some dictionaries and you can mesh anything into it that you want. But it doesn't lead to good code, because later, the more you add, the more work you would have to do in order to ensure that the data is still consistent. And a better pattern to avoid meshing all kinds of unrelated pieces of data onto the atoms is to define a kind of intermediate structure. So so previously the CIF reader, I think maybe it still does it for compatibility, it will read the space group and it will put that into the atoms object. But that doesn't really mean anything, because if you then move the atoms, you might break it and now it's a wrong piece of information. So that's not so nice. The better design is that we start with a CIF, so the crystallographic information format, I think it's called. So that's a file, and you parse it, and it returns something called a CIF block. And that block has all of the data faithfully. So it didn't really do anything, any converting, it just passed it into some Python structure. And from that you can then get anything. And you can also export an atoms object from that. And then that is a little bit advanced because it might use a space group and do some kind of symmetry mapping, so you get the full number of atoms instead of some symmetry reduced set of atoms. It's a complicated operation, so that's why one should not encode it in a single read step. And CIF is the most complicated format probably in that regard, but it affects other formats as well. So all of these formats that are not really designed to be a one-to-one representation of atoms objects, they should actually have an intermediate object that is designed only to represent a file of that type, and then a separate step to export to atoms. Then we would have much less trouble and much less like miscellaneous information floating around that we don't really know what to do with. There are also some design issues with the calculators. So we have these, so the overall design pattern is that one has the atoms and then attaches the calculator to the atoms, which enables one to do calculations. And so you say get potential energy to the atoms, then it talks to the calculator and it generates an input script, calls an external code probably, and then it retrieves and converts the data, and then you get the potential energy back. So all of that is implemented many times, and with somewhat different patterns. So commonly we have these file I/O calculators. So the ASE must generate an input file, run an external program, then read the outputs and somehow save that, and then return the requested output. And another pattern is that one launches a persistent process and can talk to it using sockets or pipes. So that allows the calculator, so for example, who talked about the socket I/O calculator the other day. That's one way to you open a persistent process with DFT code inside. And that one can communicate using sockets, and then you can control it as much as you want from the Python process. So that means it can reuse the wave functions and density every time you change the position, so it's much more efficient as long as your variations only concern positions and similar things. And finally, there are some calculators that are directly inside the Python process, which adds the, I mean, then you can do a lot of things because you can poke into the code and retrieve anything as long as there is a Python interface for it. So that's, for example, the case with the GPOR code. But it can get quite complex because if the code is parallel, then your Python process is also parallel. This suddenly imposes all kinds of restrictions on I mean, if you start opening a file, then maybe all of the processes will now open the file and you need to be careful. But when the code was written, maybe there was nobody needed to think that this might run on multiple cores. So it was just written in serial. So now you get corruption very easily unless you're very explicit about some things. And then a lot of work was done to kind of add if world.rank equals 0, then we do this. But that's also bad because if there are actually multiple calculators running inside the same world on different subcommunicators, then that will lead to immediate deadlocks and all kinds of trouble. So very difficult that. My conclusion was that the optimal strategy was to be completely unaware of parallelism and have when we cannot get away with that, we should take an explicit MPI communicator as an input. So I don't know a better solution to it. It's just a nasty problem. Anyway, so here we have a representation of most of what we have in ASE, or many of them anyway. There are all these different algorithms implemented that end up talking to a calculator underneath. So it's very nice to have this separation that we can trust that these algorithms don't reach over and talk directly to the calculator, because that means we have some level of control. We can actually limit what can happen, which then provides us with a lot of freedom to change things when we know that certain things cannot happen. But a limitation of this design is that this calculator protocol becomes very fluffy anyway, and it has encouraged the implementation of large monolithic calculators where there is a class and then a large set of methods, each using different subsets of the attributes and doing different things that should, in the end, often be similar to all the other calculators. I think I'm running a little bit out of time, so this is something that if somebody is interested in discussing this particular subject, it would be fun, but I might jump a little bit to briefly mention the ASE ecosystem. So the conclusion here is that we would like a single class that implements the flow control that makes it a calculator. And so we only have one implementation of what it means to be a calculator, and then it talks to some implementation classes that are more minimal in scope. So one of them contains system information, we call it a profile, and another contains all of the rules like which output reader and input writer, and this we call a template. A little bit arbitrary names, but that actually allows us to eliminate all of these problems, or many of them, and then maybe build something new on top. So it provides a lot of flexibility. Anyway, I want to mention also that due to the uncontrolled growth of the project, we have actually started asking most contributors of larger features to move them to separate projects, or some of them did so by themselves from the beginning. So there are a lot of projects that can kind of work together with ASE, and those we tend to call the ASE ecosystem. So these would be codes that are not limited to a particular computational code, but rather maybe works with many, or they provide some other functionality that works well and is integrated to some extent with ASE. So this can be interesting to have a look at. Then we have a lot of different communication channels. There is a good old mailing list, which was always there. And now we have a forum on matsci.org. Then there is GitLab, which we use for all of the development discussions. And there is a chat on Matrix that you're very welcome to join. And we also have the ASE bar, where we do non-serious things. Sometimes we have a beer and a video meeting just for fun. You can see the contact page. That one has everything. Previously we had IRC, so that used to be like the classical chat channel, and there were always like 3 or 4 people who never quit. But once it moved to Matrix, it actually became a lot bigger, and we have like many more active people now. Yeah. So. In conclusion, ASE is very big and has a lot of features. Many of them are very good, but if you're looking to do something that requires a little bit more, then often you can find a better specialized package doing the same job. So probably you don't want to use the ASE phonons module for very serious phonon calculations. You would use something like PhonoPy or a molecular dynamics package sometimes. Our greatest current need is to make things smaller and to do plugins. We don't really have the time, so that's why everything is stuck sometimes, if you look at the merge request list. And the final lesson is maybe that one should be a little bit aware and guard against adding things that maybe should just go into a different package. It's tempting as long as you have time to become as big as possible, but it's not sustainable. So thank you very much.
So if there are any further questions now, I think we'll have a lot of time in the afternoon as well to follow up on some things and make some good connections. But if there's 1 or 2 more questions now, I think we can do that as well. I saw Joe first.
I know one of the big discussions in Python at the minute is about removing the global interpreter lock and allowing kind of better parallelism with nested coding like, so how would that affect ASE?
ASE is not generally thread safe. I usually write code that would be thread safe, but there would be many things that are not actually thread safe. One must make use of some kind of partitioning of things in order to ensure that there is no breakage. So this means not having multiple threads using the same data at the same time, unless you are really into adding locks. But that is kind of a general multiprocessing advice. Like, instead of having multiple processes read the same data, if it's not completely, if it won't kill performance, you should probably copy the data, then work on it, and then copy it back. That kind of thing. But there is only one thing that actually uses threads in ASE, and it just uses it to parallelize some calculations over notched elastic band images, and that's a very small amount of actually threaded code.
Yeah, so I was curious to hear that you wanted to go away from a monolithic package, which I always thought of being in a way easier to maintain, to keep everything working together. We're at the other extreme, right, of having a bunch of interfaces that everybody adds on top of that what they want, which creates a lot of duplication of efforts, I think. So somewhere there's probably a sweet spot, and I would love to hear more about where you think that might be, and maybe a little bit now, and then we can continue that later in the afternoon.
Yeah, I would like to. It's a very good question, because it's too time consuming to maintain all of this, so we have to find something else. But it's also, it would be nice that we could actually improve the design before we drag it out into different packages, such that we won't break everything when we finally do it. Yeah.
ASE4.
Yes.
All right, well, in the interest of not getting too far behind the planned schedule, I think we'll wrap that up for now. We can, as I said, follow up on plenty of things this afternoon as well. So let's thank Ask again.